Okay, it's 7 o'clock. Good evening, everybody. Welcome to another Our Universe Revealed. Some new faces, young faces in the audience. Welcome. This is in the back rows. This is the public lecture series from the Department of Physics, all about the physics of the universe, whether from the small scales to the large scales. Last time, 2 weeks ago, we were talking about theories and how physicists come up with theories, talking about the standard model of physics. And neutrinos came up as a topic. And it was almost like this was a setup. It was not planned. That neutrinos are one of the most mysterious particles, newest particles, lightest particles that are streaming through you right now, but we don't feel them. And so you can almost think of them as ghost particles. And that's what Yushin is going to talk to us about this evening. Yushin joined Notre Dame in 2020, so has had an interesting first couple of years here on campus. But now we're back to in-person. It's more of the traditional Notre Dame experience. He is a professor in the physics department and works on sort of the theoretical study of particle physics like we talked about last time. He's coming to us from the University of Maryland. He was at UC Davis before that, and he got his PhD from Cornell back in 2012. And tonight, as I say, he's going to tell us all about these mysterious ghost particles, these neutrinos. So let's give him a nice warm welcome.
Maybe I'll stand here. Thank you, everyone. Good evening. It's very nice to see that many people come here to to try to hunt some ghost particles together. Okay, so that's the thing we are going to do. So I'm going to start the discussion tonight from a little bit of history. Okay, so around the 1900s, like the end of the 19th century, people begin to learn more and more about the radioactivity, like materials that emit some particles that come out from material. And a very important process, just called a name, is called the beta decay. And where the beta here is actually from today's language, it's just electron. Okay. So what they saw before is that they collect some nucleus, maybe it's carbon, for example, and they realize that after wait for a certain amount of time, there is an electron coming out from the nucleus, and also one neutron changing to proton. How do we know that? Because the carbon becomes nitrogen, like in periodic table, you move one up. Okay. So it's a very interesting phenomena. So that's why it's like the high energy physics at the late 19th century. So people begin to study this. Okay. So around the 1911, 1913, some physicists, Mattner, Hahn, and later Daniels, hopefully I pronounced this right, they realized something very weird that is going on here. Okay? So they try to measure the energy of the electron more precisely. So they make some kind of plot that's showing the number of electrons that you get versus the different energy of the electron. Okay, so just to learn about what's the typical energy of the electron. What people were thinking, what will come out in the end before, is that you should just almost get a peak of the electron, because the electron energy is just the mass of the neutron minus the mass of the proton. Right? Mass is energy, so the mass difference is the energy difference. But instead, what they found is something like show up with a much broader spectrum. Sometimes you get the electron to have a much smaller energy, sometimes you have a bit higher energy, but it's not always just a mass difference between neutron and proton. This is very weird because this starts to challenge our idea of the energy conservation. This was supposed to be a foundation of the physics laws. So what's going on? Okay. So great physicists, Niels Bohr, were saying that, oh, actually, because that was a quantum world, like people trying to have outside of the box thinking, like because the quantum phenomena looks so different. So maybe we should not stick on what we always believe is true. So he said, oh, it might be that the energy conservation is only statistically true. Like maybe when we take lots of data, it looks like it's energy conservation, but for event by event process, maybe it's not, okay? But turns out that this was soon like ruled out by the experiment due to the reason that even though I have this weird distribution of the electron energy, I always have a very well-defined maximum energy that of the electron can come out, which is basically the mass difference between neutron and proton. So this tells us that the idea of the energy conservation is still very robust, okay? Because otherwise I shouldn't have anything like this. I should just have all the different possibilities of the energy that can come out. Okay? So this doesn't seem to be a right explanation. Another great physicist at the time, Wolfgang Pauli, put out a also very crazy but much simpler explanation, which was maybe this decay process from one particle to two particle is really not like that. It's actually what happened is there are third particles that also comes out. Because if this is the case, depending on how much energy does this additional unknown particle carries, I can have a smaller energy for the electron. Okay? So it turns out if we assume that there is a invisible particle that comes out, carries energy, and the invisible particle has a mass that is close to the electron, then we can explain this kind of distribution of the energy. Okay? And this invisible particle, today we know, is just neutrinos. Okay? So these are particles that doesn't carry a charge, so that's why we don't see them easily. But they are light, and they can share part of the energy coming out from this beta decay. Okay. So Pauli is almost right, okay? The only thing that he got a little bit wrong is that he thought the mass of the neutrino should be more or less similar to electron, the mass of electron that we know. But turns out that the mass of the neutrino is way, way smaller than the mass of the electron, which I'll come back later. But of course, it's not his fault because we didn't have an experiment back then. But today we know much more about neutrinos, okay? So we just jump like 70, 80 years after that, okay? So today, of course, we collect even more data. We have seen lots of neutrinos produced at all kinds of sources. So all the way from nuclear reactor, from the sun. Sun is basically just a huge nuclear reactor. And also from a far away supernova explosion that will also generate a lot of neutrinos. So the picture that I show on the left is a photo that was taken from an old experiment, which is done at the Argonne National Lab, which is about an hour and 40 minutes drive from here. So at the 1970s, people built something called the cloud chamber that can record the trajectory of a charged particle when it passes through the box. Okay? So what we see here is that there's something that comes in, we don't see it, that ends up generating a proton, another particle we know, which is a pion, and a muon particle that comes out. And these are the particles coming out from a neutrino that hits the neutron inside this box. Okay, so we see nothing comes in, but a bunch of things come out. And that's the signal of neutrino. And today we know very well that in the so-called Snell model theory, which is basically putting all the elementary particles that we know and all their interactions, we have a very nice story about that. And is experimentally proved to be true to a very, very, very precise level. Okay, so we know these are indeed the particles in nature so far that we have seen so far. And there are 3 neutrinos exist in this big particle physics family. Okay? And they got the name of the electron neutrino because it has a tight relation and like a stronger interaction between the electron that we know. So that's why it gets the name of electron neutrino. And there is also a neutrino called muon neutrino and tau neutrino, which again is a neutrino interact more with the muon and with the tau. And these are just electron-like particle with just with a larger mass. So basically a heavier electron in a sense. Okay. So we have 3 neutrinos in nature that we know exist. But even though that we have this nice chart of the particles, put them in, we still call these neutrinos as ghost particle in nature. Okay. Because there are so many unknowns about neutrinos, and also because the neutrinos have some superpowers that make them look so different from many of the other particles. So first, so the 2 superpowers, one is the intangibility and the other one is the transformation property of the neutrino. In order to let you to appreciate the way we are going to harm the neutrino, let me just explain a little bit of what do I mean for these 2 superpowers, okay? So actually, it's a little bit embarrassed. I actually only learned about the word intangibility when I was trying to describe its property, okay? So neutrinos can penetrate through walls very easily, and it's almost invisible. And the reason is the following, okay? So thinking about like how we see things in nature, it usually comes with the electric force, okay? So I have something like when I clasp the hands together, what happened is that the electron on the skin of my hand hit another electron on the skin of the other hand by exchange of light or photon. So this is how we describe the interaction between elementary particles, which comes from by throwing a photon back and forth, basically. Okay? And the diagram like this is called the Feynman diagram. It's from the famous Richard Feynman. That is a nice way to describe the interaction. So similar to this, the neutrino can actually also interact with the regular matter or electron, but that can only throw a much, much heavier mediator called the Z boson back and forth. They do not couple to the photon or the light. Okay? It is because that this Z boson, this force mediator, is so heavy. You can imagine that when the mediator is so heavy, it's actually very difficult to transform the force, right? So that's make the neutrino interaction to the visible matter to be so weak, so much weaker. Okay. So just to give an idea, like, so if we're on the beach and then enjoying the sunshine and the photon produced by the sun will just hit the electron on our skin, so we feel the heat and feel comfortable. If it's a neutrino that comes in, it will just go through our body, okay? Because the interaction is so small. And in fact, while we are talking about the neutrino here in this room, we are constantly bombarded by neutrinos that are produced from the sun. There are about 100 trillion neutrinos that fly through our body every second, okay? But we just don't feel it, it just goes through our body, okay? And someone even estimate, okay, what's the chance for neutrino finally kick out the particle from your body? And in average, that's about once in a lifetime, if you're lucky, okay? So if you don't feel comfortable today or feel sick, I'm sure that's not coming from neutrino. Maybe your doctor don't know this, but I know, as a particle physicist, I know that's not from neutrinos, okay? And not even neutrinos can go through our body, it can actually go through Earth like very easily. It just pass through the Earth. But even so, our experimentalist colleagues has still done a heroic job in building neutrino detectors, several neutrino detectors around the world that can actually catch this ghost particles. Okay? So one very famous example is the Super Kamikande experiment in Japan. And the idea is that they buried a huge water tank, 1 kilometer underground, and filled it with purified water. So when you have a neutrino comes in, it can hit a proton in the water molecule and do that, basically that beta decay process that I described in the beginning, but do it inversely so that you go from neutrino back into a positron, which is the antiparticle of the electron. So that will generate the light. And they put about 10,000 very sensitive light detectors so that you can see that light, so you can finally catch this ghost particles. Okay. So you need something huge or lots of materials to be able to see these ghost particles. So you can imagine that even though we can see the neutrinos, it's still very difficult to collect lots of them and start to study them. Okay, so it's still hard to study them. Yeah. The other very interesting phenomena of the neutrino that, at least for the particle that we see in nature so far, this only happens for neutrino, is that they can transform. Okay, and this is a purely quantum effect that will show up mainly in neutrinos. It's just unfortunately, because of limited time, I actually cannot explain to you why this happens. Okay, it's probably like 1 or 2 lectures in the grade level particle physics class. But for here, I'm just going to describe what happened. Okay, so just to give you an idea, it's not hard actually. If I have time, I'm sure you can all catch it. It's just that I don't have that much time here. Okay. So what happened for this neutrino transform is that if, let's say, in a experiment, I produce one type of neutrinos, let me say a muon neutrino, okay, and let this neutrino to propagate through certain distance. This neutrino will end up changing into the other type of neutrinos, either the electron neutrino or tau neutrino. They will transform between different type of neutrinos. Okay, and these neutrinos are just, it's not that I just put out the name, so I call them differently, so I claim they are not different. It's not, because these different type of neutrinos have well-defined interaction to either more to the electron or to a muon or to tau. So they literally just changes from one type of neutrino to the others when they fly for a certain distance. So this process is called the neutrino oscillation. It changes from one type of neutrino to the others in space. So we actually now measure this phenomenon very precisely. So what we do is that this is just an example using it's actually still being built. It's almost done. It's an experiment called DUME, which is at the Fermilab. Have any of you visited Fermilab before? Oh, very good. Yeah. So it's about 2 hours drive from here. They just reopened from all the pandemic closed. So you should find time to go and visit. Okay? So what they do, or they are going to do, but the same idea already exists in many other experiments. I'm just using it because they provide a nice picture I can use directly. So what they do is that they produce a muon neutrino at Fermilab, and then let it to fly 800 miles away to hit another underground target in South Dakota. Okay? So that they can measure for the amount of muon neutrino that they produce initially, how much neutrinos becomes electron neutrino after traveling 800 miles away. So using this property of the neutrino oscillation change, they can actually measure the mass difference between the 3 different neutrinos, because it turns out this quantum phenomenon is totally determined by the mass difference between different neutrinos. Okay. Again, I didn't explain to you why, but that's just the case. Okay. So by doing this measurement, we can find the mass difference between neutrinos, but this is different from knowing the mass of each individual neutrinos. That we don't know, okay? But at least we know the mass difference between them. And if you are interested about this Dune experiment and also this neutrino oscillation story, you can also contact our local expert, Professor Laura Fields. She is actually one of the members in this Dune experiment. Okay, so this intangibility that tells us it's so hard to collect lots of neutrinos together to study them. Is the reason why there are still so many unknowns about this ghost particle, and also partly the reason why we call them the ghost particle. Okay. There are things that we know very, very precisely about all the other particles we have been seeing in nature so far. We have no clue. We have not much clue for neutrinos, for those properties. Okay. So, for example, with some reason, okay, anyway. So, for example, we don't actually know, as I just said, we don't actually know what are the masses of these neutrinos, even though we know the mass difference. So we're really trying to measure their mass. Okay, that's a holy grail question. If you can do that, I think it would be some Nobel Prize thing, okay? Because it's so hard to find their masses, individual masses. Okay? Also, we don't quite know if neutrinos actually have some ghost interactions that only work between each other. Okay, and let me explain this question. Okay, what do I mean? Okay, so if you are asking me that, can there be any other unknown interactions between two electrons that we don't know yet? Okay, I can tell you, well, from all our experimental measurements so far, if that force exists, if there is a fifth force or some new force exists, it needs to be about 100 million times weaker than the electric force. Okay, otherwise we will have seen it in the experiment already. Okay, so this is how precise that we know about the interaction between two electrons. But if you are asking me the same question about neutrinos, I will say, well, we don't quite know, but from the some neutrino facility experiment or collider experiments that we have before, that's probably, I mean, we shouldn't have an additional force that's larger than 10% of the electric force. So this means there's still a large room for neutrinos to have some secret interaction by themselves, but we still don't know yet. This shows how little we know about this, the interaction between neutrinos. Okay. And a related question is that how long can neutrinos live? Because again, for all the particles we've been seeing so far, the heavy particle can decay into lighter particles. Okay, so they disappear. Okay. And we have been able to measure all the lifetime of all the particles that we have been seeing in nature. With the two only exceptions is the photon, or the light, which doesn't have a mass, so it doesn't decay. And the other one is the electron. Okay? We actually don't know if the electron can decay, maybe it cannot, but we can experimentally check that. Okay? So today we know that if you do experiment, we know that electrons can live at least for 10 to the 29 years. Okay, that's just from some experimental measurement. And this is about 10 to the 19 times longer than the age of the universe. So we really know that electrons shouldn't just disappear one day. Okay? But again, if you ask me about the same question about neutrinos, just from the this neutrino experiment, kind of this measurement we had before, we only know that it needs to live more than 100 microseconds. If it's after that time, I have no clue. I don't know what's going on. Okay, so this again tells you how little we know about the fate of neutrinos. So as I'm going to show you, well, I'm going to tell you that if I take the cosmology into this game, start to look into things in the early universe, I can improve all this knowledge about neutrino by a lot. Okay? So that's the thing that we want to look into. for the rest of the discussion. Okay. By the way, for all these numbers, I put the reference in the very end of the slide. So just in case if one of you want to dig out the numbers, I told you where are these numbers from. Okay, it's not just, I'm not lying to you. So just okay. So let's try to use the whole universe as a neutrino detector. Why? Again, because even though this neutrino experiment and collider experiment are very powerful in producing energetic neutrinos and doing a precise measurement, they don't produce lots of neutrinos. It's not enough that we can have a bunch of neutrinos here and then study them. Okay. For example, for that Dune experiment I just told you, okay, they can produce about 1 neutrino per centimeter cubic, just stay there for 0.1 nanosecond. After 0.1 nanosecond, they just fly away. Okay, so they only spend time in 1 centimeter cube region for 0.1 nanosecond. So this is not enough time and not enough neutrino to study their interactions. And in fact, just here right now around us, we actually know from our understanding of the Big Bang physics that we know quite well due to various observations. We know there are in average about 50 or 60 neutrinos per centimeter cube just around us. They're just here. Okay, if you draw a 1 meter big box, there's about 60 million neutrinos inside here. Okay, sometimes they come out, sometimes they come back. But in average, we have this many neutrinos around us. Okay. If you're interested, I can explain more how do we know this, but this is what we know. So how are we going to use them? How are we going to use the fact that the universe actually has lots of neutrinos here? How can we use that to study the property of these ghost particles? Okay. So the thing that we are going to use, which I will spend most of the time in the rest of the talk, is we are going to use the so-called cosmic microwave background to study these neutrinos, the behavior of neutrinos. Again, another question. How many of you have heard about CMB and then, oh, very good, okay. Okay, so actually one thing that I feel very excited about giving this talk is I get to project these large CMB maps on this big screen so that it looks like we're on the CMB background. But for people who haven't heard about CMB before, you might wonder, I mean, well, why is it fun to look at this thing? It just looks like some colorful background noise from your TV, right? So in fact, what we are looking at here at the CMB is literally how the universe looks like about 400,000 years after Big Bang. So it's about 14 billion years ago. This is basically how the universe looked like. The red dots here are the higher temperature regions in the early universe. And the cold region here is just, the blue region here is just the lower temperature region. And because early universe is just a hot, dense plasma soup, okay? So it's not surprised that this soup has some waves, right? So some region is more hotter and some region is colder. And that's basically what we see here. It's a pretty boring structure. I'm sorry, I mean, for the so long ago, but that's because it's a time before all these galaxies, they only start to form, but not to the structure we see today, okay? And why do I say that this thing is the picture at this specific time, that 400,000 years ago? Why do I say that? Because there's something very important that happens at that time, which is that the charged particle, like a proton and electron, begin to be able to catch each other and form a neutral hydrogen, so that the charged plasma that can originally trap the light from escaping from the charged particles now allows the light to come out. Okay, so this happens around the 400,000 1,000 years ago. So only since then, we can see this light come out and propagate to us, so we can see this image today. So this is really a snapshot of the universe at that time, okay? And the reason why we call this a microwave background is because the universe keeps expanding, so it stretches the wavelength of the light into a longer and longer wavelength. So even though in the early universe, the temperature is much higher, today their wavelength is only 1 millimeter, and the temperature is about 2.7 Kelvin. Okay, that's a very low temperature. I don't quite remember how to translate into a Fahrenheit, but it's a low temperature. Okay. Okay. So this is the thing that we see, and we have a Planck satellite, which is a satellite experiment, can take a very nice picture of this. Okay? So this is the most high precision measurement of this the CMB background. I'm going to call this a CMB just so that I don't always repeat the name. Okay, so then the thing we are going to figure out is if I have neutrino in the universe, or I should say, comparing to the universe that does not have neutrino, how would the image of the CMB be different from each other? So, okay. Once we know this, we know why we know there are neutrinos in the background given by this image, okay? So let's now begin to do some work, okay? But it's simple, okay? I shouldn't scare you. Okay, so let me just pick a small patch of that image, okay, and put it here. So now let's put this cute ghost particle in a universe. Assuming this is the image from a universe, from some parallel universe that doesn't have neutrino, but now let's add some neutrinos into it. Then see how would the image change. Okay. One thing that will change for this image is that the hot region and the cold region will look bigger in the sky. Okay. And the reason for this is the following. Okay, this is a very a little bit rough and hand waving, but this catches the idea. Okay, so the reason for this, the reason why the hot and cold spot becomes bigger, is because neutrino is a very light particle, so they basically travel with the speed of light. They move very, very fast. Okay? But the wave, the plasma wave is like the water wave that even though they propagate, because there are massive particles inside that make the wave, their motion is much slower than the speed of light. Okay. So if you have this plasma wave propagating in the early universe at that time, neutrino will always move ahead of that wave. So what they will do is that they are in front of those plasma waves, so their gravity, they generate a gravity to pull that wave to move faster. Okay. So when you have a fast-moving neutrino, they are going to make the plasma wave propagate faster, and therefore, with the same amount of time that you can generate image, the spot will look bigger. Okay, does that make sense? Okay, just because the gravitational pull from neutrinos. The other thing that the neutrino will do, again, this is the type of thing that it's not hard to understand, but I also don't have enough time to explain, but I will just tell you what happened, is that when we have neutrino in the early universe, it's increase the total energy of the universe and make the universe expand faster. What that will do is that allows the light to have relatively more time to scatter around, to diffuse around. So that's going to smear out the contrast between the higher temperature point and lower temperature point. If you can imagine the photon just keep scattering around and then bring like a kind of equilibrate the temperature between point by point. So the image you will see when you have a neutrino will have a slightly lower contrast in this image. Okay. So this is the effect if the universe has neutrinos in it. And turns out this is exactly what we see for the observation, CMB observation that we have comparing to the universe that doesn't have neutrinos. And we can actually use this to identify there are actually 3 types of neutrinos that does exist in the early universe that makes the image looks more like this. Okay, so we know neutrinos exist. Okay, so the CMB image tells us there should be fast-moving neutrinos around to change the image in this way. And we can apply the very similar idea to the other questions that we are trying to ask about neutrinos. Okay? Because when we ask, can there be secret interactions between neutrinos? We'll say, well, if you have secret interaction between neutrinos, that means neutrinos can bump into each other, right? So if you want neutrino to move from left to right, the scattering would make it move less from the left to right. Okay, so the scattering between neutrinos will make the neutrino propagate slower. Okay, and again, we just said that the data wants to see fast-moving neutrinos. So the image that we see does not like this. Okay, so that's why using the same knowledge of comparing the map with and without neutrino, we can actually say that if there is additional interaction that for these ghost particles to hang out together, that interaction needs to be billion times weaker than the electric force. Okay, remember what I told you before from the Collider experiment, I can only say this needs to be 10 times weaker, but now it's actually, we know it actually needs to be billion times weaker. So it's a much, much better measurement. Okay. And a similar thing happens to that we can do for the how long can neutrinos live, because if neutrinos decay into other particles too quickly, I can have these other particles come back, have an inverse process to produce neutrino every now and then. So if you ignore these other particles, only look at neutrinos, it looks like neutrino got deflected and no longer move in a straight line. Okay? So this is another thing that can slow down the neutrino. So the data, again, the data doesn't like it. So using the CMB measurement, we now know that neutrino needs to live longer than about a year, which is still not a very impressive bond comparing to electrons, like a 10 to the 28 years. But still, it's much better. Okay. Okay. So, and we can also I want to end in a few minutes, but before that, I want to say that we can also actually have a chance to measure the mass of the neutrinos. Remember, even though we know the difference between the neutrino masses, we don't know what's the individual neutrino mass, and we really want to know that, okay? And turns out the CMB measurement can also give us some clue of that, okay? So there's one very interesting phenomenon of this CMB image. I didn't describe it like very clear before, I mean, partially lying, which is that when the light can finally come out from the charged plasma, when the neutral hydrogen were formed, they actually didn't go all the way to us in a straight line. Because on their way to us, there are dark matter clumps. Okay, dark matter, again, is this is for the whole additional talk. It's a heavy, is some kind of the energy density, the mass density we know exists, but we don't quite know about these details. But we know they can clump into structures. Okay? So when the light passing through these dark matter clumps, the gravity from the clumps is going to bend the light a little bit, okay? So when the light having this bending every now and then, the direction they are moving is now got this, changes a little bit, okay? So it's not all the line just goes straight to us today. They actually got like a change of direction a little bit. So what that will do is they are going to smear out a very sharp edge between the hot and cold spot. and maybe make it look more like smooth on the boundary. Okay, and this we can also measure. Okay, we do see this experiment. Okay. So if neutrinos are massive, what will happen is that since these are massive particles, they have mass and they move very fast. You can imagine like you do a hard work to build some dark matter clumps here, but then you have a massive particle that just fly through. This particle is going to attract some of the mass and tear the dark matter clump apart, right? So the existence of the neutrino and with a certain mass is going to reduce the size of these dark matter clumps. And if that happens, the light can just go more directly to us. So the image will become sharper, okay, comparing to before. But sorry, I should say from the beginning, like this image, I just show it kind of do some Photoshop thing to show you the image in idea. It's not really I'm showing you the picture, because for the actual picture, it's more difficult to see by eye. So I just enlarge the effect by quite a lot. Okay. So this gravitational lensing effect tells us that we cannot have neutrinos to be too massive. Okay, otherwise the image will become too sharp, and this is not what we see from the observation. So this ends up telling us that give us an idea of how heavy the neutrino can be. Okay, so unfortunately, the current data is not precise enough to directly tell us very precisely what's the mass of each neutrinos, but it does tell us that whatever neutrino mass that we have, it needs to be about 10 million times lighter than the electrons. Okay. So even though it's not the solution yet, but at least we start from knowing nothing about the exact neutrino mass to the knowledge that it needs to be lighter than 100 million times lighter than the electrons. And in the next decade, there will be a next generation experiment that taking this photo of the CMB has a chance to really just measure the neutrino masses. Okay. So we have certain confidence about that. Not 100% guarantee, but we know that may likely to happen. Okay. Actually, I lied about it. The last thing I want to say is the previous one, but here, let me just say one more thing, okay? So this last slide, before I conclude, is actually what my work ends up contributing to all these stories, okay? But I'm only going to mention it very briefly, just with one slide here. Okay? So another way that I can use the whole universe to hunt this ghost particle and measure their property is to use the so-called large-scale structure of the universe. Okay? The image I'm showing you here is the distribution of the galaxies in the visible universe. So the size of this is about 1 billion light years, of order 1 billion light years. And each pixel, each bright pixel that you see here is one galaxy. Okay? So we are just basically one dot somewhere on this picture. Well, we are here because we look away from us. Okay? Our galaxy universe doesn't look like this butterfly shape. The reason why this is dark is because these are pointing to the directions that are more noisy along the Milky Way disk. So we just cut out this region. But you can see there's a non-trivial structure that shows up with the distribution of galaxies. And this structure basically follows the structure of the dark matter distribution in the universe, and which is called the large-scale structure. So the visible particle just follow the distribution of the dark matter and form this kind of a gigantic net, like a web kind of a structure. Okay. So this gives us a chance to do a similar measurement I told you before, that if neutrinos have some mass and then they travel around and they destroy the dark matter clumps, we are going to see the effect. We can also do a similar measurement using a large scale structure. Okay. And the exciting thing is that we will soon launch a new experiment called the Euclid satellite that can do this kind of measurement with a much, much better precision. And part of my work is to show that once we have knowledge, we can get a much better knowledge about neutrino mass and lifetime. For example, we do have a chance to constrain the neutrino lifetime starting from the 1 year that I told you before and improve it to 10 billion years, which is the age of the universe. Okay, so we can do that. I mean, if the measurement is as good as we hope to. Okay, so let me conclude. Okay, so the important message I want to leave here is that the cosmology can be used to observe these ghost particles, these neutrinos, very precisely, especially for a certain type of properties. Okay? We get more understanding about their masses. We can check are there secret interactions between neutrinos or not. And also we have a better chance to know how long can neutrinos live. And in fact, this story about neutrino is just one of the many stories that we know that how we can use cosmology to study particle physics. It looks like two very different things from the beginning. Usually you think about cosmology, you build LHC, like a particle colliders to do a careful check of the particles. But it turns out that we can also learn a lot by using cosmological observations. And the exciting thing is that there will soon be many, there are lots of ongoing next generation cosmological experiment that is going to operate in the next few years. And this will soon give us a much better data than give us a more chance to see even more invisible physics in the coming decade. So stay tuned. Okay. Thank you very much.